accidentally there was a pause button on the recording which was clicked and a lot of stuff was skipped, so I will just cover it up. So I think it was somewhere supposed to be here. So if I, so the differential of this function, any function f, so these are the only two variables, we can change this and this. So I can write something like this, and if I take a differential of f, I don't know, it will be something, uh, but I have to also consider the constraints. So n1 plus n2 will give me capital N, that's for sure. And also, thanks to the Hawley physics, I also know that energy should be conserved with some fluctuations here and there, but I don't care about the fluctuations. So uh, so basically epsilon 1 times n1 plus epsilon 2 times n2 will give me the full energy. And if this is constant, and if I multiply some constant on both sides, this quantity will still be constant, and I have to consider that while finding minimas of a function. So I just substituted this beta, and spoiler alert, this beta actually later comes out to be this in StatMath, and I don't want to talk how, where, how, what this came from, because I myself suck in this. So now I just put all, so I have a dn1 here, tiny differentials, tiny differentials here, tiny differentials here, tiny differentials everywhere. So I just add all of those constraints with taking the tiny differentials common. And once I do that, and of course when I differentiate it with respect to n1, I just get minus log of n1. Similarly this, and you just do this, just find n1. This is what you get, n1 and n2, and you can find alpha easily, because you know that n1 plus n2 is n, and you know n1 n2 value, and you get alpha. And finally you found number of n1s and number of n2s. So number of n1s will be just n times number of, if instead of this I use 1, number of n1s will be just n times, just write 1 here, this, and number of n2 will be similarly, instead of I you just use 2. And for any number of particles with energy I, if I want to find its probability, I have to just do small n I by n, number of particles with that energy divided by total particles, and the below it, whatever the sum I am doing, like e power minus beta epsilon 1 plus e power minus beta epsilon 2 plus e power, if I have those epsilon 3 and so on. And remember, all of these ni's are of the order of 10 power 23. There are a lot of them. If you don't have a lot of them, then I don't think statistical mechanics will even have its purpose. This large numbers is what allows us to take those approximations and come up with these crazy results which match with experiments. So almost match with experiments, of course, to good extent, I think. So that's it, and you get this partition function. Yeah, that's it. Finish. Bye bye.